All right, in this video, we're going to go ahead and start to talk about ways, again, that we could improve upon the linear approximations that we did previously and start to update these to quadratic approximations. You'll see down here in the picture that I have below that we are going to see this blue curve e to the x that's on here, kind of like what we sketched above. And here's our tangent line from problem 1. And it has the formula 1 plus x, right? And we know that on a small enough interval, right? Like if I only view from here to here, I can't really see any difference between those two functions. Of course, if I look farther to the left or farther to the right, I can clearly start to see the gaps emerge. But you'll notice here that e to the x almost kind of looks like the shape of a parabola. Maybe just if like this one side just kind of bloop fell over. So maybe there's a quadratic that I could use to model this. And you'll see here that I have written down a quadratic that I believe does work. I think this formula here would work perfectly fine. I think that's a perfectly reasonable formula to use. But the question would be, how did I come up with that formula? If that models this pinkish purple line, you'll notice that this thing does a little bit better at approximating for maybe a little bit longer. Not much longer than what the line did. If the line works well between the red bounds, the parabola works well between the x bounds. It was able to go a little bit better for a little bit longer. So our question would be, how did I come up with that parabola equation? So here's what I'm going to go ahead and actually write down in order to try to justify this. I'll say this. It seems that we need a quadratic, which we'll call again P of x, that has the same tangent line at x equals 0 as f of x equals e to the x. Like that's definitely one thing I would need to be true, right? I definitely want to have the same tangent line at x equals 0. So the curve's kind of moving in the same direction. But I also can say something else about this quadratic. I kind of want it to make sure that it's bending maybe in the appropriate way. Because of course I didn't have to draw a quadratic that was opening upward. I could have drawn one that was opening downward. But you would probably expect that if I draw one that's opening downward, that's probably not optimal because e to the x kind of looks like an upward parabola. So I want to say that I also want the same, quote, bend, or what we call concavity, as f of x near 0. So if these are the things that I want to be true about my quadratic, I could think about how I could summarize these in a couple different points. So I'm going to go ahead and write out some different properties that I want to be true. Here's, I think, property 1. If I want to make that same tangent line occur, it definitely has to be the case that when I plug 0 into my function f, and I plug 0 into my new quadratic formula, they have to produce the same thing, right? Because I need the same starting point that I have down there in the picture. I'm also going to need a second property. To get the same tangent line, I'm going to need to have the derivative evaluated at 0 for my function be equal to the derivative evaluated at 0 for the quadratic. Because if I don't have the same starting point and I don't have the same starting slope, I will never get the same tangent line. And if I want to get the same concavity, you might be able to think back to Calc 1. How in the world do I determine the concavity of a curve? Well, yeah, if I want the concavity to be the same, I would need the second derivative to ultimately be equal at that particular point. So the question is there ever going to be a polynomial that could meet these descriptions? Well, I don't know, but we could at least maybe start with the following. We know P of x would have to be equal, if it's going to be a quadratic, to something in the following form. It's going to be equal to something that looks like this. Now, there's a special reason why I'm going to write things in this particular way, but at least you might be able to compare this to equations of quadratics that you've seen before. I'm always going to have some number of x squareds, some number of x's, and some constant at the back. Again, I'm going to just have my c's here. They're going to stand for constants. I've just kind of labeled them as c1, c2, c0, as opposed to using different letters like an a, b, and a c. Now, part of the reason that I've done this is to bring about an interesting connection. We'll notice that the subscript on the c matches the power on the x that it goes with. So c2 is with an x squared, and c1 is with an x to the first, and c0, I guess that's with an x to the 0. Now, I have no idea what any of these constants are. I guess pretty much any of them, except for c2, could be a 0, right? So maybe there are no extra x's here. Maybe c1 is a 0, and I can find that out. But what I'm going to do is try to figure out, could I determine what those three different c's are there that could make these three properties true? Okay, so here's how I'm going to start. I'll start with this. Okay, so I'll say that using the properties above, so that is my green properties, I think I can start to state the following. I know that p of x again is going to look like this. Okay, that's my p of x. But I know that I want p of 0 to be equal to f of 0, right? That was my first criteria up here. So really quickly, I could start to see, wait a minute, what is p of 0? Well, if I plug 0 in for all my x's, the only thing I'm left with there is c0, whatever that constant is at the back. And apparently then this needs to be equal to f0. So what I found here is a formula for what that constant at the back of my polynomial, the back of that quadratic, needs to be. Okay, let's look at the second property then. The second property talks about the first derivative. So I'm going to try to take the derivative here of my polynomial. Okay, don't panic about this. It's really easy. Remember, x is our variable. So I'll start with, what's the derivative of c0? Well, if c0 is a constant, its derivative should just be 0. It should just disappear. What's the derivative of c1, which is just a number, times x? Well, that should just be c1. And the derivative of c2 x squared should just be 2c2 times x to the first, right? I'm just using little power rules. But of course, we saw here that when we go to that formula and we plug in 0, we want that to be the same answer as what f prime of 0 is. So let's see what happens. If I plug 0 in for x, what would I get back? Well, c1 is what I would get back. And if I want that to be f prime of 0, then again, I just found a little formula for what that c1, what that coefficient of x to the first needs to be. I'll go ahead and do one final check here, which is on that third condition, which talks about a second derivative. So let's take a second derivative. What's the derivative of c1 with respect to x? Well, that would just be 0 again. The derivative of 2c2x is just 2c2. It's just a number in front of an x. And again, I know that I want p double prime of 0 to be equal to, well, let's see, if I plug 0 in, there's no x's in that formula, right? So there's nothing I can go ahead and actually replace with 0. So this is just 2c2. And I want that to be equal to f double prime of 0. So notice I don't have a formula yet for c2, but it's pretty easy to find one. Because if I just took both sides of this and divided by 2, I would have a formula for c2. So I can write out the following conclusion. That polynomial that I need, that quadratic, which I know looked like c0 plus c1 times x plus c2 times x squared, has to be equal to, well, let's see, c0 is f of 0, c1 is f prime of 0, and c2 is f double prime of 0 divided by 2. That has to be the formula for creating this quadratic. Okay, so that's like a super weird formula that I have there, but I'm going to box it up because it's super valuable for us. And I still don't know if that formula kind of coincides with this formula over here in the picture. But let's actually try that. And we can try that out in the next example in the next video.